Welcome back, everybody. Today we're going to be talking about subspaces. So let's get right into it. Assumingly, let's say you have a vector space and it consists of the set A, B, C, D. Okay, now let's look at a set X. We say it contains A and B. Now we know that if we have a vector space V and we have a subset, let's say our subset is X, then X is a subset of V, right? Only if the elements of X and V are shared. We can't say that X is a subset of V if the elements in X are, let's say, 1 or 2, because 1 and 2 are not part of our vector space. So that's how we know we have a subset, right? So for a subspace, we need to have X as a subset of our vector space V. So let's say X is a subset of our vector space V. Now, how do we consider it to be a subspace? Well, in order for a subset, which is what I have right here, the notation that we use for a subset is that X is a subset of V. So for X to become a subspace, we need to have 3 conditions that we can check off as true. So the first condition is, let me just erase this. So the first condition is that our X, which is again a subset, cannot be empty. We cannot have X as an empty set. So X can't just be nothing. It has to have elements in it. The second condition is that for all elements of X, so let's say we have an element M and P that are part of our subset X, right? So if M and P are part of X, then M plus P are also part of X. And this symbol just means part of, right? So if M and P are part of X, then M plus P must be part of X. So if X is equivalent to 1 and 2, then that means 3 must also be part of X, whereas 2 plus 1 is 3. Now the third condition is that for all scalars, so the way we write scalars is C, that is part of a real number. So C is a scalar, R is just real number. So for all real numbers, this is how you can read this if you have something like this. For all real numbers, and for all M that are part of our subset, right? So for all real numbers and for all M or elements that are part of X, C times that element must also be part of X. So if X is equal to M, or let's say M is 2, then 1 times 2, so that is 2. And then 2 times 2, so that is 4, must also be equal to, must also be part of X. So if this is again 2 times 1, so 2 is initially part, then 2 times 1, and 2 times 2, and so forth, must also be part of our X. So this just means, if I were to kind of summarize this, our X is a subset and it becomes a subspace if and only if it is not empty and if it is stable with addition and scalar multiplication. So scalar multiplication is just the third condition. And when we say stable, that just means if U and V are part of our X, that means U plus V are also part of our X, right? So if 1 and 2 are part of your x, then 1 plus 2 is also part of your x. And I have represented this right here. Just going to erase this. Now, we can also look at, moving forward, another useful thing is that initially we learned that zero vector, so zero vector is represented like this. So 0, if our vector space is represented by M, let's say M is our vector space, then we would write 0M, right? So this just means the zero vector. So whatever is denoted here should be matchy-matchy with your vector space. I just wanted to point that out because it's going to be useful for our proposition. Now, the proposition we're looking at right now supports the 3 conditions because you can use these 5 conditions in total either to prove that you have a subspace or either to prove that you do not have a subspace. So the first condition is that X is a subspace of our vector space if and only if it satisfies 2 conditions. So the first condition is that 0 vector will be part of X, right? So X, we can have blah, blah, blah elements, I don't know, M n elements, but we must also have 0 as part of X, right? So if 0 is in there, then you're good. And then the second condition is that for all scalars, so for every real number, and for any 2 vectors k and m that are part of our subset, scalar times k plus m are also part of our subset. So if for any given scalar, for all scalars that are part of, for all scalars, so 1 to infinity, and so let me just do the and symbol here, and for 2 vectors, any 2 vectors k and m that are part of X, any scalar times by the first vector plus the second vector are also part of X. So if my scalar, let's just say it's 4, k is 1, m is 2, okay, then that just means 4 times 1 plus 2 is also part of our X. Right, so that's just 4 plus 2, which is 6. So 6 is also part of X. And let's just say that my set X consisted of initially k, which is 1, and 2. We know that it consists 3 because 2 plus 1, right? Remembering that u, v is also part of X if u and v are part of X. This is from a previous condition. So now they're saying, well, 6 is also part of it, and 0 is also part of it. So these 5 conditions will help you prove or disprove that a specific subset is a subspace or it is not. So just knowing these 5 conditions is very, very helpful. And that's pretty much it for today's video. Again, if there's a question that says disapprove or prove that X is a subspace, well, if you're wanting to prove that X is a subspace, whatever information is given to you, you want to use that, right? You want to obviously seek out, usually it's very easy to see if 0 is part of X. And then again, if it is very clear that 0 is not part of X, that just means a condition is not met. So it is not a subspace. Another useful thing is that all 5 conditions must meet. It can't be like 3 conditions meet and then 2 don't meet. Then it's only a subset. It's not a subspace, right? If all 5 conditions meet, then your subset becomes a subspace. Okay, that's it for today's video. We'll see